So after we introduced kernel PCA, we are now in shape to look at different unsupervised learning techniques, and the simplest one are clustering approaches. I will start with the k-means algorithm because I assume that you all know about this algorithm. Perhaps something that you do not know is that k-means can be seen as an optimization method that iteratively minimizes an objective function. So given data points x1 to xn that live in Rp, what k-means is doing is that it alternates between two steps. Given a set of centroids, k-centroids that are vectors that represent the data, there is an assignment step that will assign every data point to the closest centroid. Then the next step consists of considering a cluster of points that are assigned to a specific centroid and updating the centroid by taking the mean of the points in the centroid in the cluster. So this can be justified by an objective function that each step will minimize. So overall, this will be at the end an optimization problem which is intractable, but what we can show is that each step of the k-means method will decrease the value of the objective function. So consider the following objective, which operates over assignments that are these variables Si that are simply indices going from 1 to k, such that for a data point I, if Si is assigned to j, it means that the point I is in the cluster j. And then we also optimize over a set of centroids that are represented by these vectors mu j, one per cluster. So the following objective makes sense. It sums over the data points the squared norm, the squared distance between each data point xi and a well-chosen centroid mu si, such that many points share the same centroid, meaning they are in the same cluster. So now assuming that the centroids are fixed, they are given to you. How would you minimize this objective? You will simply, independently for every data point, assign each xi to the closest centroid, meaning that the si is simply the argmin over the indices of the distance, the squared distance between xi and mu s. So this is the classical assignment step of k-means, and it's easy to see that this given fixed centroid, this step will decrease the value of the objective function. Now, what is the next step? The next step consists of averaging the points. But in fact, we will see that it's in fact equivalent to minimizing the objective given fixed assignments. So assuming that you are given assignments, S1 to Sn, then you can decrease the value objective by minimizing over the squared distances for the points that live in cluster J, such that you can update the centroid J. So mu J is obtained by minimizing this quadratic function. So here, note that this is a sum over the points that have been assigned to cluster J. So minimizing a quadratic function, we have done that many times. So you could tell me, well, let us do gradient descent or different approach. But in fact, this is a quadratic function that has a very nice shape. It's very simple. And if we compute the gradient of the objective with respect to mu, and if we consider the linear system that simply sets the gradient to 0, it's easy to see that in fact we have a closed form. The closed form is consists of simply taking the mean of the points. Basically, the centroid update consists for every centroid J, assigning the average of the points that have been assigned to this cluster. So Cj here denotes the set of indices that have the label J. Okay, and again, because we see that from an optimization point of view, given fixed centroid, we minimize with respect to assignment, and here, given fixed assignment, we optimize with respect to the centroids. So we can alternate, and every step will decrease the value of the objective. It does not guarantee you that you are going to find a global objective, because in fact, it can be shown that the problem is intractable. But if you are lucky enough, you are going to find a good local solution. And very often, k-means work relatively well. It's actually probably the most popular approach to cluster data. Okay, so why did I present things from an optimization point of view? My motivation was not to make things more complicated. It was because so far, each time we have introduced kernels, we started from an optimization objective. And now that we have done that, it's actually very natural to extend this to an RKHS where we send the data. So given data points, x1 to xn that live in some set X and a positive definite kernel K, we call H the RKHS. And what is the new objective? Well, the objective is the same as before, but we make tiny modifications. The first modification is that we send the data to the RKHS through the kernel mapping file. The second important modification is that now centroid is a point in the RKHS, and the norm, of course, becomes the RKHS norm. So can we do something similar, which is to do alternate minimization between the assignments and the centroids? Implicitly, we can do something like that, something very close to that, and this will give us what is called the kernel k-means algorithm. For that, we need actually a small proposition. Remember that in the regular k-means method, when we updated the centroids, we had to minimize the quadratic function over points that live in a set. And more generally, these were optimization problems of this form, except that here the phi of xi were simply equal to xi. Now, when we consider the most general case of an RKHS, we would like to know what is the solution of an optimization problem of this form, where we want to find a centroid mu that will minimize the squared distances to some data points. So here, to simplify, I consider all of the data points. Of course, we are going to consider subsets in a few slides. And then it turns out that we can show that the center of mass, which is simply the mean of the phi of xi, is in fact the solution of this problem. So this is a good news. It means that we are going to do things very similar to k-means. Each time we are going to update a centroid, we are going to take the mean of some points. So how do we show that? If you wanted to show that from an optimization point of view, you will need to introduce the concept of differentiable functions that live in some RKHS. It's not exactly something that you like. We can do things that are much simpler, simply by playing with the notation. Consider indeed your objective function here. And we simply want to find a vector mu that minimizes the sum of squared norms. We know that because we have this norm and the corresponding inner product, we can simply extend these quadratic functions such that we get here a sum of the norms of the phi of xi that are independent of mu. On the right, we have the squared norm of mu. In the middle, we have the cross inner products between the phi of xi and mu. And we use here the bilinearity of the inner product to put the sum inside these terms here. We are quite lucky because naturally we have this quantity here, this average, this mean of the phi of xi, which is exactly the center of mass that we have called phi n, such that we can simplify this into this second line, which is, here we simply have -2 times the inner product between phi n and mu. And now we use basic properties again of the norm and the inner product, simply to rewrite this second line as the difference of two terms here. On the right, we have the distance between phi n and mu squared, minus here the square norm of the center of mass. Now a question for you, how do I minimize this objective here with respect to mu? Of course, this is minimum for mu equal to the center of mass. So this is a very simple statement, but it's important because it allows us to simply extend the K-means method to kernel with kernels. So given now the objective, which is here, this is the kernel K-means objective. We know that given assignments Si, the optimal centroids are the center of mass of the respective clusters. Then we can update what we call the kernel K-means. It's called the greedy approach. Why greedy approach? Simply because it turns out that this optimization problem is actually also difficult to solve. And when we have a difficult problem to solve, either you use a local approach or you use a method that has an exponential complexity, but that can give you the exact solution, or you solve a different problem. So far, the kernel K-means is simply a local approach that will start to minimize iteratively this objective. Okay, so how do we change K-means into kernel K-means? Well, we alternate between two steps again. A step here is the centroid update. So given assignments that are given to you, S1 to Sn, you update the centroid by minimizing this objective for every cluster. So here now the sum is over the points that are in each respective cluster. And we know that the solutions of that simply consist of taking the center of mass. So this is a way to parameterize the centroid, simply given the assignments. So now that we have this center of mass, we can also do the cluster assignments, okay? Because given previous centroids, given fixed centroids mu1 to mu_k, that are center of mass from previous assignments, we are going to try to improve the assignments. So we are going to assign each xi to its closest centroid by simply, so these are independent optimization problem that we are simply going to compute k values for each data point. So this is a simple problem. This is, of course, a simple problem if you can express this as the manipulation of kernel values, meaning if you can use the kernel trick. But remember that it was a long time ago. Maybe in lecture 2, the first kernel trick that we introduced was to compute distance functions. It was also about computing barycenter. So we had formulas that were very similar. So let us do it. So let us consider a center of mass defined on clusters from the previous step. How do I optimize this over the set of indices? Well, I have a square norm that involves lots of phi of xi, phi of xj. As usual, what we do is that we develop this quadratic term. And if you are not convinced, just take 5 minutes again at home to check that this is correct. You get indeed a sum of kernel values. So this sum involves here a double sum of the kernel values that are inside the cluster S. Here you have a sum of kernel values for J being in the cluster S. The only part that depend on S are these two terms. The first one here is simply the square norm of the phi of xi. So it's independent of the index. Okay, so all operations are performed by manipulating kernel values only. And implicitly, it tells us that we are, in fact, optimizing an objective of this form over assignments. Why over assignments? Because we know the closed form for the center of mass. So this is, in fact, another view of the kernel K-means objective, where we plug the closed form solutions for the centroids, and we need to find the optimal assignments. So you see that here, this is a combinatorial problem. In fact, finding an optimal assignment for every data point. And if we don't like the objective in terms of kernel values, in terms of points in the RKHS, we can also rewrite it in terms of kernel values. So now we could stop here because you know the recipe for kernel k-means. And in fact, if you want to implement it, you have everything here to do it. Now, it turns out that if we do a bit more of manipulations, we can obtain another equivalent objective, which I think is very interesting from to get additional intuition about what it means to do clustering with a kernel function. So let us do it. There will be a few steps that require some brain gymnastics. These are not things that are complicated. These are just manipulating sums, inverting sums when we can do it. But you will see that the result will simplify greatly the objective function, and it will also pave the way to other approaches. So that's what we're going to do now. So the term in blue on the right, which is here, it turns out that if it's a term that involves some kernel values that are inside the cluster Si. And if you count the number of times each of these terms appear, involving as well this normalization factor here, which is here, by the way, I didn't mention it, but this is simply the size of the cluster CSI. So if you sum over every cluster and you look at this kernel value, how many times it appears in the sum, what is the factor which is in front of it, you can get convinced that this is equal to the quantity on the right. So on the left, we sum over the data points. On the right, we sum over the clusters. And in fact, what I'm claiming, it's actually not very complicated, but it's just hard to follow if you want to do the computation in your head right now, that this sum over quantities that depend on data points is equal to the sum over clusters, which involve these double sums of points that live in each cluster. So CL here is a cluster L, and we have simply here the normalization with the size of the cluster. Why do I do that? Simply because if I look also at the middle term at the middle term in red, so let us simply look at remove the -2 in front of it and look at this. This is also a sum over n over the n data points. And if you play the same, what I call brain gymnastics, then you get the same quantity. It's not completely obvious, but again, if you ask yourself this specific kernel value in the sum, how many times it appears, what is the factor in front of it, overall at the end, you get that this is equal to this quantity that involves a sum over clusters. Okay, so that means that we have, in fact, when we sum over all of the data points, we can start simplifying it. So how do I obtain this new kernel k-means objective? Let us come back to the previous one. What I do is that I remove the term on k of xi because it's independent on the assignment. So it doesn't change the solution if I remove this term. Here, when I say that I get -2 a quantity plus a quantity, it means that this objective becomes the minimization of minus this quantity. So I don't like to minimize minus a quantity. I prefer to maximize this quantity. This is exactly what I get here. So the kernel k-means objective is in fact equivalent to the following one. We maximize over the assignments this sum over the clusters, where we normalize here by the size of the clusters of the double sums inside each cluster. So you see that it's interesting because it gives us some intuition about what it means to do k-means with a kernel. What we want is to find a partition of your data points that maximize the mass inside the cluster. When I say the mass, it means you take your kernel matrix. Let's say you do a permutation of your data points such that each point that are in the same cluster are next to each other. What we want is to maximize the mass in the kernel matrix, which is inside the blocks that correspond to each clusters. And if you need some precision with that, we can also draw some examples during the interactive session. So this gives us some intuition. And here we really see that this is about really ordering the columns and the rows of the kernel matrix, maximizing the sums over diagonal blocks. This is really a combinatorial problem, which in fact can be shown to be NP-hard. And here comes a bit of classical recipes to address combinatorial problems. Well, when you have a combinatorial problem, either you use a greedy algorithm. This is basically kernel k-means, or you change the problem to something that you can solve, and you hope that the solution of this different problem will be useful to obtain a good solution of the original problem. And this mechanism is called a relaxation. And in fact, there is an approach called spectral clustering, which can be seen as a relaxation, as a spectral relaxation. I will precise what I mean by that, of the kernel k-means objective. So you may see spectral clustering in other classes from a very different point of view. And in fact, there is not a single algorithm which is called spectral clustering in the literature. But for me, I like this point of view because personally, the first time I understood spectral clustering was by looking at the kernel point of view. Because here I like to have a specific objective. And naturally, when you relax this objective into something slightly different, it really gives you an algorithm, which is the spectral clustering algorithm. So that's why this part is important, because spectral clustering is also something very popular in the literature. And for me, it's a very natural way to do clustering with a nonlinear metric, or also to do clustering with non-Euclidean data. So that's why it's important. So you will see that this is a bit technical. So if you cannot follow the technical details in real time, at least try to get the big idea, which is you start with a combinatorial objective like this, and we are going to change this into a different, slightly different problem. We try to make as few modifications as possible to turn it into something we can solve. And it turns out that this something we can solve will be an eigenvalue problem. So let us now introduce some notations. Again, I don't want to introduce notations to make things more complicated. I want to make things simpler. So something which is simpler to introduce when you consider a clustering method is an assignment matrix, which we call A, which is binary. It has n rows and k columns, and the rows sum to 1 because you need to assign each data point has to be assigned to at most a single point. I mean, it has to be assigned to a single cluster. You see here that we have this rescaling factor. This is a bit unfortunate because it will make the notation a bit more complicated. So feel free to ignore it in your head if you have difficulties to follow. But formally, we will need to introduce a diagonal matrix of size k times k, where the diagonal entries are basically equal to the inverse of these quantities, this 1 over the size of the clusters. Another way of seeing that, using your new notation, is that the diagonal elements of D should be the inverse of the sum of the columns of A. So again, what is the sum of the columns? They correspond to the size of each cluster. Okay, so this is the inverse of the cardinality of each cluster. Now, it turns out that given the kernel matrix K, which is of size n times n, it is possible to simply rewrite this problem here as the following one, So this is in fact very easy. It's just playing with notations. So it's easy to do it quietly on a sheet of paper. It's just hard to do in your head. But in fact, if you ignore the matrix D, you can try to interpret what it means to multiply A transpose times K times A and take the diagonal elements of this matrix by the trace, sum the diagonal elements, you will see that you get exactly this sum over the data points that leave the sum over the kernel values corresponding to data points that live in the same cluster. And the role of the matrix D is to introduce this rescaling factor here, which is the inverse of the cardinality of the clusters. And then we optimize over the assignment matrix, over the diagonal matrix under these two constraints. The first one is that A should be binary and the rows sum to 1. And D is simply the constraint that D should be diagonal and the diagonal entries should be the inverse of the cardinality. So far, this is simply introducing notations, matrix multiplication notations, that gives a formulation equivalent to the top one. So now you will see why we do that, why we don't like to play with these double sums, why we use this trace operator. It's simply that what we're going to do is to consider this optimization problem on the top, which is hard to solve. Look at the constraints star and double star and relax these constraints to make the problem simpler. And by making the problem simpler, we hope that we don't modify too much the problem, but we make it simpler and we turn it into something we can solve. This is the principle of relaxation, which is very classical in optimization. So if we look at the constraints that we have on A and D, it turns out that it's easy to show that the square root of D times A transpose A times the square root of D is equal to the identity. So if you have a hard time to follow this, remember that A is an assignment matrix. So at least what is easy to see is that A transpose A is diagonal. And in fact, it's also easy to see that A transpose A is a diagonal matrix that carries the cardinality of each cluster on the diagonal, such that if you rescale by this square root matrix on the right and on the left, you get the identity. So the constraints, star and double star, they imply this. So then a natural relaxation consists of saying, well, I'm going to drop the constraint star and double star, but I'm going to keep this constraint, which is simply a consequence of star and double star. In other words, what you do is that you replace the original constraints by a consequence of these constraints. So you are, of course, you are not solving the same problem, but there is still a relation between this consequence and the original constraints. And now we will have an objective that only depends on this matrix D, which is A times the square root of D, such that the problem on the top, we are going to replace it by the maximization over this matrix Z, which is of size n, so number of data points times k, number of clusters, of the trace of this of Z transpose k times Z, such that Z transpose Z should be equal to the identity. And again, I'm going to ask you to remember your old linear algebra classes. Well, it turns out a solution Z star to this problem can be obtained by computing the eigenvectors of k associated to the k largest eigenvalues. And if you remember, we had seen something very similar for kernel PCA. And it's more than very similar. This is actually kernel PCA, computing the eigenvalue, the eigenvectors associated to the largest eigenvalue of the kernel matrix. is what you do when you do kernel PCA. So what we show here is that kernel PCA is related to a relaxation of the kernel k-means objective, which is a clustering objective. And this is interesting because it shows that there is a relation also between PCA and the clustering problem. Now there is a question for you, which is, while we have relaxed the kernel objective, we turned it into something that we know how to solve, which is an eigenvalue problem. And after you obtain this matrix Z, which is of size n times k, how do we obtain a clustering? Because Z is simply a matrix. Okay, so how do we obtain an approximate solution A of D of the original problem? From the exact solution of the relaxed problem. So we call this solution Z star. This is, and for that, it's not something obvious, in fact. So something you can do, okay? You can simply observe that Z is related to A up to a normalization factor. So with the original constraints on A, every row of A has a single non-zero entry, which is 1. So naturally, what you can do is to simply take Z and binarize it, meaning you compute the maximum entry of every row of Z star, and you call that the assignment. And what does it mean in terms of principal component? Because if we talk about principal component, it will mean that we will assign each data point to its, basically to its closest principal component. Closest, mostly in the sense, we'll assign a data point to the principal components, which is the most aligned with this data point. So formally, it's very simple. You take the matrix Z that you obtain by solving the eigenvalue problem. And for every row, you keep only the maximum entry. So this is a perfectly valid approach. And sometimes this is called spectral clustering. But it turns out that there is something which is in fact more classical and which is even more effective. Because you see that this is not, binarizing is fine, but it is not perfect because we don't really take into account, the fact that there are clusters that are larger to each other. So in fact, what is also very classical is to consider that this matrix Z star, it provides us as well a low dimensional representation of every data point. So a row of Z star is a vector of dimension k, which corresponds to the projection of the data point onto the k principal directions. This can be seen as a representation, as a representation of the data in a Euclidean space, such that what we can also do is that consider these representations of the data points that you can also possibly normalize and apply the traditional k-means algorithms on the rows. And this is called also spectral clustering. It's actually more popular to do this approach. And so we did things that were pretty complicated to, at the end, obtaining something very simple. Spectral clustering is the same as doing kernel PCA, representing your data points as low dimensional vectors, and do the regular k-means algorithm on these low dimensional vectors. So it's very easy to implement, but you see that the path to start from this complicated combinatorial problem to this was a bit complicated. And yes, the third answer is that you do something else. Do another variant of the previous procedures. I told you there is not a single spectral clustering algorithm in the literature. This is also one of the reasons why. Okay, and I'm going to now continue this part by discussing briefly something called canonical correlation analysis. So I'm pretty sure that many of you are not aware of the regular canonical correlation analysis. it's sad because it's actually a very interesting unsupervised learning approach, which is useful in many contexts when you have different views of the same data. So I'm going to start introducing it. You will see that, and there are many interesting things to do, in fact, with this CCA approach. So consider now two views of the same data sets. So what is a view? Let's say it can be two views representing the same things. It can be, for example, image and text audio that will give you three views of the same scene. It can be, for example, if you do data acquisition of the brain, it can be EEG and MEG, different types of modalities that acquire the same, that observe the same phenomenon. And what is the goal of CCA is also to reduce the dimension, also to find directions in these different views, but you want to find directions that are maximally correlated. Basically, you want to find directions, let's say in your audio data, that are very consistent with directions in the video data or in the image data. And there is a natural way to formulate it. So this is the classical way. So you assume that the data sets are centered. Okay, you can, if the data, it's something we always do for PCA because the concept of directions is more useful if the data is centered at 0. And what it means to find views that are maximally correlated, well, our two directions in the regular CCA are parameterized by directions WA in the first view and WB in the second view. Note, by the way, that these views have different dimensions. Okay, X here is a matrix in P times N, and Y is a matrix in D times N. And you are going to look at the projection of the first view onto WA and the projection of the second view onto WB. That gives you these projection coefficients, WA transpose XI. Here I assume, by the way, that the W, I mean, you can also assume that the W are normalized in some way, but let us maybe forget about that at the moment. So we get these projection coefficients, and the correlation is simply this sum divided by n of the coefficients for every data points I. So xi, again, represent a view of a specific point I, while I represent another view of this point I. And we have also this normalization factor here, which, to be justified, can be seen here simply as the variance of the projections. Okay. So assuming that the pairs xi, yi are RID samples from an unknown distribution, in fact, this what CCA does is to maximize over WA and WB the covariance of WA, the correlation of, basically it's the correlation of WA transpose X and WB transpose Y. This is why we normalize by the variance here of the projections. And so after I say that, it seems that, well, I'm simply defining an objective that do what I want. And that to apply this in practice, I need to work a bit more. It turns out that it is, again, it can be seen as an eigenvalue problem, which is called a generalized eigenvalue problem. So I don't want to do a full course on CCA, so I'm giving here a reference. You can look at this nice book by Shaw Taylor and Christine Yanni on kernel methods. On section 6.5, you have all of the technical details. I'm going still to give you some of them in the next slides, but it's simply important to know that we can solve this sort of optimization problems. What I want to insist on is that this gives the first pair of what we call canonical directions. And if now you're familiar with PCA, what you do to find the next directions is that you repeat the optimization problem, but you add the constraints that your new directions should be orthogonal to the previous ones. And it turns out this can be also solved using this generalized eigenvalue problem. Okay, so let us work a bit with this formula. So let us consider this part of the lecture to be optional. You can accelerate it. You can accelerate the video if you find it a bit hard to follow. But if you are interested in this, let us look at the details. If we remove these sums and prefer to work with matrix notations, the previous problem is simply the maximization of this WA times X transpose Y times WB divided by these variance terms. It turns out that you may notice as well that there is a scaling ambiguity here because we are interested in directions. But in fact, if you find a vector WA, WB that are solutions, if you multiply WA by a scalar and WB also by a scalar, it doesn't change the objective, such that you can also remove the scaling ambiguity. And among the solutions of this problem on the top, focus on the ones that are the following ones. You simply maximize WA times X transpose Y times WB, such that the variance terms are equal to 1. And the solutions of these problems are also solutions on the problem on the top. Why we do that? Simply because it will be helpful to simplify the problem. It turns out that when we have an optimization problem like this one with constraints, we know that there exist Lagrange multipliers lambda A and lambda B, such that the penalized problem is in fact provides the same solution as the constraint problem. Of course, you don't know in advance what is lambda A and lambda B, but you know that they exist. And by the way, I also don't like to maximize problems. So what I do here is that I minimize minus of the previous objective. Of course, it doesn't change anything. And here on Lagrange multipliers, lambda A and lambda B, I will put here inside the constraints. Okay, WA transpose X WA minus 1. And here the same with WB. The factor 2 is here only to simplify the interpretation of lambda A and lambda B, but it doesn't change anything, because if there exists a lambda A and lambda B such that this provides the same solution as the original problem, you can simply call that lambda prime A, lambda A over 2, and this lambda B over 2, you can call that lambda prime B. So without changing the solution, I can assume I have this factor 2. But how do I proceed now? To get more information about my problem, I will consider the previous objective, compute the derivatives, and say I want the gradient to be equal to 0. So now you should start getting familiar with taking the gradient of quadratic objectives. Okay, look again, this is not any types of objective. This is a quadratic objective with respect to WA and WB. So if I do that with respect to WA and WB, what I get is a set of linear systems. So saying that the derivative with respect to WA is equal to 0 gives me the first linear system. And if I do the same with WB, I get the second linear systems. Now, I want still to get more information about it. So far, it doesn't tell me much. What I will do is to simply multiply the first equality by WA and the second equality by WB transpose, multiply on the left. And it turns out that if I subtract the two resulting equalities, what I get is that lambda A times this variance term is equal to lambda B times this variance term with respect to B. And because remember that at the solution, these variance terms are equal to 1, it means that I know that lambda A necessarily is equal to lambda B. So I can call that lambda. And this is nice because now that I put lambda here, this set of two linear systems on the top, I can write it as the set of linear systems on the bottom, which if you open a textbook on linear algebra, you can now call that a generalized eigenvalue problem. Remember that if you have a matrix, let's say a matrix A times W equal to lambda times W, then this is an eigenvalue problem. Here it's a bit different because you have a matrix times W equal to lambda times another matrix times W. This is why it's called a generalized eigenvalue problem. But we can work a bit more and reduce it explicitly to an eigenvalue problem that you know already. For example, called sigma A, this matrix that contains the cross inner products between X and Y. Sigma B, you call the correlation matrix that contains the X transpose X and the Y transpose Y, and W is the vector that concatenates WA and WB. If you assume that these matrices sigma B are invertible, so we are going to do that here, but you can be very rigorous even if they are not. It requires a few additional details that I'm skipping here. The generalized eigenvalue problem, you can simply rewrite it as the lambda times, remember that was sigma A, the one on the previous slide was sigma A times W equal to lambda times sigma B times W. If I multiply by the inverse square root of sigma B on the left, I obtain this new relation here. And if I do now a small, if inside between sigma A and W, I introduce the inverse square root of sigma B times the square root of sigma B, what I get is indeed an eigenvalue problem, which is what I wanted to do, which is here I get this matrix on the left, and between parentheses, I get a vector, and I want this to be equal to lambda times this vector. So that means that the inverse square root of sigma B times W has to be an eigenvector of the matrix which is on the left. And now you know how to implement it. So it's good for you. There are also many other things to say, but you are going to discover them in the kernel framework. In fact, what I am skipping here is that there are a few issues with this approach, which are not obvious at first sight, but which are becoming obvious when we work with kernels. Now, let us come back. Let us stop the part that I called optional about technical details, and let us come back to the part which is interesting, which is we have a formulation for CCA. How do I use kernels with CCA? How do I define kernel CCA? So if you have in mind the way we changed PCA into kernel PCA, it will be easy, because having two views of the data, meaning you need to define two kernels. You have two positive definite kernels, Ka and Kb, that operate on the same data. Or two views for a single data set x1 to xn is now the set of the phi A of xi and the phi B of xi, where phi A is the kernel matrix, the kernel embedding of the kernel Ka, and phi B is the kernel embedding of the kernel Kb. Both of them are sending the data to two different RKHs, HA and HB. So this is what it means to do also kernel CCA. Here we have two kernels and we are sending the data in two different RKHs. And we can do now something very similar to kernel PCA and define the following formulations where the directions both live in their respective RKHs, FA and FB, and we want to maximize the correlation between the projections, which are defined by the coefficients, the inner product between FA, the direction, and phi A of xi, the view A of xi, and on the other side, we have phi B of xi and the direction FB. So remember that if you use the reproducing property, what it also means is that kernel CCA is trying to find something like that, to find two functions, FA and FB, in two different RKHs that are such that the evaluations FA of xi on the data sets are maximally correlated. This is an important intuition here to get about kernel methods. The directions are functions that take input data points and provide a value. And here we want simply to maximize the correlations between these values. And by the way, if you consider the same RKHS, HA, and HB, if you consider basically the same kernels KE and KB, you recover PCA. So it's so there is nothing strange about all of this. So kernel CCA is just a bit more general. So now up to a few technical details. So I want simply to accelerate to give you the main results. You can apply the representer theorem for these previous problems because these were optimization problems that take as input these functions, that takes as input the FA of xi's and so on, such that we can parameterize our two directions FA and FB as a linear combinations of functions Ka of xi and beta A and Kb of xi. And by playing with these kernel notations that you are now very familiar with, we can introduce the kernel values and the product between these coefficients alpha and the kernels, and here the coefficients beta and the kernel matrices. Such that this gives us to this maximization problem over alpha and beta, where alpha and beta are two vectors in Rn. Again, we have a scaling ambiguity for alpha and beta. If you multiply alpha by a scalar, you do not change the objective, and the same for beta, such that we can restrict ourselves to a solution that satisfies this set of constraints, such that the variance terms on the bottom are normalized. So it's actually a simpler formulation. We maximize the product between alpha, Ka times Kb times beta under these quadratic constraints. And we can now proceed and try to work on this. If you open your linear algebra textbook, you realize this is also a generalized eigenvalue problem. So that's good for you. And the subset, because you can solve it simply by using any solver that is able to solve these types of problems. And the subsequent canonical directions are obtained by solving the same problem, but you add orthogonality constraints, the same as for PCA. Now, this is a question for you here. What is wrong? I'm telling you, this is very wrong. There is something really, really wrong about all of this. It doesn't mean that I lied to you. It means that I have omitted to say a few things. So let us try not to omit it and work a bit on this problem to get an interpretation. So assume that Ka and Kb are invertible, which is pretty reasonable. If you take a Gaussian kernel, it will be, unless you have identical data points, it will be invertible. Then make the change of variable alpha prime to be equal to Ka times alpha and beta prime to be equal to Kb times beta. Then we can solve the problem with respect to alpha prime and beta prime and then recover the solutions with respect to alpha and beta. If you do that, look at the problem on the top. What we get is that we are now maximizing over alpha prime and beta prime, alpha prime times beta prime, such that the norm of alpha prime is equal to 1. This corresponds to the term at the top here. The norm of beta prime is also equal to 1. It corresponds to this term. And we want to maximize this inner product. Now, I'm telling you that this looks really wrong. Why? Because if I take any vector alpha prime, well, I can maximize this by simply selecting beta prime equal to alpha prime. So that means that the kernel canonical correlation analysis formulations admit an infinite number of solutions that are arbitrarily irrelevant. Meaning if I take a direction alpha prime in the first view, which has nothing to do with the data, I can find a direction in the other view, which maximizes the correlation. So this is really, really bad. So why do we have this, and how do we fix this problem? We can call that a spurious correlation. Spurious correlation means that you have so much data points that you can find, you can find data that correlates to each other, but which have nothing to do. So here the phenomenon is a bit different than the classical spurious correlation phenomenon, but I still like to give you these classical examples simply because if you don't know this website, it's a website which is good to know. There is a website that looks at lots of data and finds correlations. So for example, you can find that, the murders by steam, hot vapors, and hot objects is very correlated with the age of Miss America. It simply comes from the fact that you have lots of different data and you find stupid correlations in there. This is also a nice one. The worldwide non-commercial space launches is heavily correlated with sociology doctorates awarded in the US. So it's really a stupid correlation, but it exists. And if we come back to our problem of kernel CCA, there is a problem of spurious correlation, which is slightly different. It's more a problem of overfitting and numerical stability. Basically, when I say if you take any alpha prime, you can find a beta prime that maximizes the correlation, it means that I can find any vector alpha, any function in the original RKHS, and find another function that maximizes the correlation. But in fact, remember that from the start of this class, we are not interested in any function in some RKHS. We are interested in smooth functions. And I can tell you that if you take a smooth function fa and you will not find a smooth function fb in the other RKHS that maximizes the correlation if fa has nothing to do with the data. So this is a way to solve the problem, is to add additional regularization. So it consists of replacing these variance constraints here by one that also penalizes the norm of FA in the RKHS, and similarly, you will also penalize the norm of FB in the other RKHS. If you do that, you restrict yourself to smooth functions, and then you find functions that are relevant. And it's very important to do. If you don't do that, kernel CCA does not work at all. It simply produces garbage. So that's a last example of application of CCA that I like to show. It's now a relatively old paper where we have two views, images and text. And in this paper, kernel CCA is applied to find a low-dimensional representation of the input data, which is consistent with both images and text. And it's pretty elegant to do that. And I encourage you to look at this paper. So I don't want to spend too much time on kernel CCA, so I will not comment much more on this. But I will be happy to answer any question during the interactive session. Okay, so that's it for today. And next time we are going to discuss the kernel jungle.